Module 2, we're going to start talking about the nature of graphs. So we're going to spend a lot of this module talking about graphs. But first, we're going to talk about symmetry in section 1. So before we can talk about the different types of symmetry, we have to go over even and odd functions. And these are going to be different than even and odd degree functions. They are different definitions. So for an even function, we have a function is even when f of x equals f of negative x. So what that means is that you're going to replace every x with negative x and get the original function. We are going to plug in negative x for x. You're going to simplify it, and if it simplifies back to the original function, then it is an even function. So for an odd function, its definition is a function is odd when negative f of x equals f of negative x. So what that means is you have two steps. You have to first multiply your function by negative 1. Okay. Then you're going to do the second case. You're also going to then replace every x with negative x. And if those are both the same, then it's odd. So for a function to be odd, multiplying it by negative 1 is the same thing as replacing every x with negative x. They both end up being the same. So now that we've defined even and odd functions, we're going to go ahead and look at the types of symmetry. So we're going to talk about 3 types of symmetry. We're going to talk about a graph being symmetric about the x-axis, y-axis, and origin. To test to see if a function is symmetric about the x-axis, we're going to replace y with negative y and try to get the original equation. And if you can get the original equation, then you have symmetry about the x-axis. So when you're looking at a graph of a function, it's symmetric about the y-axis. This would be an example of something that's symmetric about the x-axis. If I flip what's in the first quadrant over the x-axis and it lays directly on top of my function, then it has symmetry. Now, by definition, something that is symmetric about the x-axis is not actually a function, since it fails the vertical line test, but an equation can still have x-axis symmetry without it being a function. Next, we have symmetric about the y-axis. So to be symmetric about the y-axis, you replace every x with negative x and try to get the original equation. And if we compare this to our definition of an even function, it's pretty much the same thing. We're replacing x with negative x, and we're getting the original, which means anything that's symmetric about the y-axis is an even function. So I know even functions follow this rule. And it can be said the same way. If a function is even, then we know it's symmetric about the y-axis. So it can go in both directions. So an example of something that would have symmetry about the y-axis, the most common example is a quadratic. Those have, well, the parent function of the quadratic, I should say. Not every quadratic has symmetry about the y-axis, but the parent function does. So if I take the left side and flip it across the y-axis, it should lay over top that right side. Last symmetry we're going to talk about is symmetry about the origin. So there are two things you have to do to test to see if something is symmetric about the origin. You have to replace x with negative x, and you have to replace y with negative y. And then it follows the same as before, and then you try to get the original equation. So it's not exactly written as the same as the definition of an odd function, but I can say, any function that is odd is symmetric about the origin. So odd functions are symmetric about the origin. And this, you can do it vice versa. If a function is odd, you know it has to be symmetric about the origin. So an example of something that has symmetry about the origin is the parent function of the rational or reciprocal function. It is symmetric about the origin. If I were to take what's in the top right and flip it over the origin, it would lay over top what's in the bottom left. So odd functions are symmetric about the origin. Even functions are symmetric about the y-axis, and no type of equation is symmetric about, no function is symmetric about the x-axis because it would fail the vertical line test. One thing I should make clear is that a function cannot be both even and odd, which means by definition, a function can't have both y-axis and origin symmetry. So it can't have a function that's both symmetric about the y-axis and the origin. However, I can have a function that's both symmetric with the x-axis and the y-axis. An equation can have multiple symmetries as long as those two symmetries aren't the y-axis and the origin, because that would mean the function is both even and odd, and a function cannot be both even and odd. So I could have x-axis and y-axis symmetry, I could have x-axis and origin symmetry. I can't have all three. So you can't have multiple symmetries for an equation. You can't have a function, though, that is both even and odd. So let's go ahead and test some functions to determine if they're even, odd, or neither. So a function, so if we remember from the front, a function is even when f of x equals f of negative x, and a function is odd when negative f of x equals f of negative x. Since both of these tests involve finding f of negative x, that's always going to be my first step when determining if a function is even, odd, or neither. I'm going to find f of negative x first. So if we're looking at f of x equals x squared plus 12, I'm going to find f of negative x. So I'm going to replace every x with negative x. I'm going to get negative x squared plus 12. Now, negative x squared is negative x times negative x, which is the same thing as x squared plus 12. So I get f of negative x equals x squared plus 12, which is my original function f of x. So I don't even have to test to see if it's odd, because right away I know this function is even. Looking at my second example, f of x equals x cubed minus x plus 1. So I'm first going to find f of negative x. So I'm going to have negative x cubed minus negative x plus 1. So negative x cubed is negative x times negative x times negative x. I have an odd number of negatives, so it's still going to be negative, and then x times x times x is x cubed. So I'm going to get negative x cubed minus a negative x becomes plus x, and then I still have plus 1. So f of negative x is negative x cubed plus x plus 1, which is not our original function f of x, so I know it's not even. So now I need to find a negative f of x to see if it's odd. So negative f of x is when we take our function and multiply it by negative 1. So negative 1 times my function x cubed minus x plus 1. So I go ahead and distribute my negative. Negative f of x is going to equal negative x cubed plus x minus 1. And it's really close, but it is not identical to f of negative x. So it is not odd, which means this function is neither. The last example here is f of x equals x over x squared minus 1. So first we're going to find f of negative x. So we're going to have negative x over negative x squared minus 1. So f of negative x, well, negative x is going to stay in the numerator. Negative x squared is going to become x squared, and we still have minus 1. So close, but not the same thing as f of x, so it's not even. So that leaves us with checking negative f of x. So negative 1 times x over x squared minus 1. So remember, this is negative 1 over 1. So when I multiply it, I only multiply the numerator by negative 1. So it becomes negative x over x squared minus 1, which is the same thing that we got for f of negative x. So it does equal f of negative x. So we have negative f of x equals f of negative x. So this function is odd. Last thing we're going to do is determine symmetry. So we're going to go ahead and look at f of x equals x squared plus 12 again. And we've already determined from above that the function was even. So I know it's an even function. And from the front, we know that even functions are symmetric about the y-axis. So I already know that this is symmetric about the y-axis. And because it's symmetric about the y-axis, I know it can't be symmetric about the origin. So we're just going to double check to see that it's not also symmetric about the x-axis. So to see if it's symmetric about the x-axis, I'm going to go ahead and write it as y equals x squared plus 12. And to check to see if something's symmetric about the x-axis, we replace y with negative y. So we get negative y equals x squared plus 12. And if I divide both sides by negative 1, I'm not going to get y equals x squared plus 12. So I know it's also symmetric about the x-axis. So the only symmetry it has is symmetry about the y-axis. Our second example is xy equals 15. So we're going to actually test for all three symmetries with this function. And we're going to start with x-axis symmetry. So we're going to go ahead and replace y with negative y. So instead of xy, we're going to have x times negative y equals 15. I can rewrite that as negative xy equals 15. This is not my original function xy equals 15. And even if I were to divide both sides by negative 1, it wouldn't become xy equals 15. If I were to divide both sides by negative 1, it would become xy equals negative 15, which is not the same thing. So I know it is not symmetric about the x-axis. Next, we'll check to see if it's symmetric about the y-axis. So y-axis symmetry, you replace x with negative x. So we're going to have negative x times y equals 15. Well, negative x times y is the same thing as negative xy equals 15. And as we saw before, this is the exact same thing we got from when we were testing for x-axis symmetry. So I know that it's not going to be the original function, so I know it's not symmetric about the y-axis. So last thing we have to check for is symmetry about the origin. So symmetry about the origin replaces x and y with negative. So we're going to have negative x times negative y equals 15. Well, because I'm doing a negative times a negative, I know it's going to be positive. So negative xy, negative x times negative y is the same thing as xy, and then it's still equal to 15. And this is our original function. Our original function was xy equals 15, so it does have symmetry about the origin.